My name is Chris Sabins. This is my Labview project, which is to control the height of a ping pong ball. On the right, you can see this little diagram of the main setup being used, which at its simplest is a system consisting of a fan, a tube, and a ball. The ball is inside the tube, and when the fan is on, it sends air up the tube, and the ball is carried up with it. The question is, how could we be able to select some position within the tube and then be able to control the fan such that the ball stays at that position? So, how is this problem going to be solved? The idea is to create the sort of system shown here. The user will give the system a set point, the position the ball is desired to be at. The actual current position of the ball will be measured by a sensor, and this will be subtracted from the set point, giving what's called an error value. This error value will go into the controller, which will somehow figure out what power level to give to the fan, here controlled using a technique called pulse width modulation, which will be discussed later. Once the power level of the fan changes, the position of the ball ought to change, which will be in turn measured by the sensor again, and will go back through the cycle over and over as the controller guides the ball to the set point. The sensor being used to measure the position of the ball is a Vernier motion sensor. The code to incorporate this sensor is already provided, so little has to be done programming-wise to use this sensor. The sensor is mounted at the top of the tube so that it measures the position of the ball relative to the top of the tube. The fan being used is a squirrel cage fan powered at about 11 to 12 volts. The fan is quite strong, so it doesn't need much power to lift the ball up. The mount here used is pretty important, as it is vital that the tube be kept straight and kept in position so that the sensor, which is not bound to the tube, can actually see all the way down. One of the most annoying things about this project was that if the ball fell to the bottom of the tube, which was frequent, there would be some kind of vacuum effect on it, and the ball would get stuck at the bottom no matter how hard the fan blew. This required a way to easily get the tube out from on top of the fan and then quickly put back into perfect position. The mount shown here allows this to be accomplished pretty well. The technique being used to control the power sent to the fan is called pulse width modulation. It is exactly what it sounds like, with the fan being turned off and on again with pulses of current. The width of the pulse, called the duty cycle, the percentage of the period when the fan is turned on, governs how much power the fan gets. Obviously, if the fan is only turned on 50% of the time, the fan receives precisely 50% of the power it would have gotten if it was turned on constantly. By varying the duty cycle of these pulses, the power sent to the fan can be controlled very precisely. It is important, however, that the frequency of these pulses should be at least 20 kHz. Below that, the motor will stall. I also find the duty cycle, at least in my particular setup, should be at least 30% on. Below that, and the fan will also stall. It seems that raising the frequency allows the fan to run on lower duty cycles, and I run the fan at 40 kHz, but it doesn't look like going at a higher frequency than that makes any more difference. 30% looks like the minimum. This is the physical circuit used to control the fan. The pulse width modulation is achieved with the use of this MOSFET. The voltage source in the bottom left corner comes from the DAC, a counter signal that flips between 5 and 0 volts. The MOSFET works by acting as an electronic switch, letting the current flow from the top terminal to the bottom terminal when on, which happens when the middle terminal receives 5 volts. When the MOSFET's off, when 0 volts are given to the middle terminal, no current is allowed to pass. There are some other intricacies associated with the MOSFET, and it doesn't work technically exactly as described. In other circuits, for instance, it might behave in a different manner. But in this circuit, that's how it behaves. It is also important to mention that if you want to use a 5-volt signal to turn the MOSFET on, you have to use an IRL MOSFET. The one I'm using is an IRL 520. Other MOSFETs, specifically IRF MOSFETs, require 10 volts for them to fully turn on, and I wasted quite a lot of time trying to control this circuit with an IRF. The other thing worth mentioning in this circuit is that the use of a diode put in reverse across the fan. This is called a flyback diode, and it's necessary because when the motor is switched off inside the fan, it generates a voltage in the reverse direction across itself. And as the fan is being switched on and off about 40,000 times a second, it is important to give that reverse voltage somewhere safe to go. The diode allows it to simply flow back across the motor. Without any further level of control, just using the techniques of pulse width modulation and manually turning the fan off and on again, not much can be done to accurately position the ball. One of the reasons for this is that this system is inherently unstable. At any given time, there are two forces on the ball, gravity pulling it down and the air pushing it up. The force of gravity is of course constant, and the force from the air, for any particular power setting, also turns out to be constant. This means that if the fan is left on at any particular power setting, then the net force on the ball will be constant, and the ball will therefore either accelerate up to the top of the tube or fall down to the bottom, except of course when the net force is precisely zero. The consequence of this is that it is impossible to simply assign each position the ball could be at to a particular duty cycle and simply map the desired position to this duty cycle. The system is more complicated than that and requires a constant increase and decrease in duty cycle to keep the ball steady, constantly accelerating the ball in alternating directions. This cannot be done without computer controls. I did spend a lot of time trying to control the ball this way by seeing if it was possible to control the ball without any pulse width modulation at all. This is what happens if you try and turn the fan off and on at very low frequencies. In this case, on for about 4 seconds and then off for 1/10 of a second. Even after being off for only a very small amount of time, the fan loses all of its inertia and has to be completely turned back on again. This effect is the reason why the frequency has to be so high. Here at least the ball is able to oscillate back and forth across the whole length of the tube. But without a computer, this is the best that can be done. The ball must be controlled by a computer. How exactly will this be done? The goal for the computer is to approximate this yellow curve shown here, called an ideal step response. This is a position time graph, and both curves represent the position of the ball. The point in the graph where both curves start changing is when the set point changes. So you can imagine the ball is hovering steadily in one spot, and then upon the changing of the set point, the system immediately starts trying to move the ball to the new point. Ideally, shown in yellow, the ball just teleports to the new set point and stays there with no change. Obviously, that's impossible, but in any case, the goal of the controller is to try and get as close as possible an approximation to the yellow ideal step response. This approximation might look something like the pink curve, which is kind of like the ideal step response, but with attributes that make it less desirable, such as overshoot, a non-zero rise time, and even in some cases, a steady state error, where no matter how much time is given, the ball will always be off by some constant amount. What options are there for designing an algorithm to produce this step response? The one I use is called PID, which computes the output of the fan by calculating the result of the expression on the bottom of this slide. You take 3 elements of the state of the system and in a way linearly combine them, which is to say you multiply these 3 elements by 3 constant terms, Kp, Ki, and Kd, and then add the results of each together. These 3 elements are the error term, which as mentioned previously is the difference between the set point and the true position of the ball, the integral of the error term relative to some small period of time preceding the current state of the ball, and the derivative of the error term. Taking these 3 terms, multiplying them by their respective constants, and adding them together gives an output value which, although somewhat arbitrary, should give some information about what to do with the fan. The promise of the PID algorithm is that for any sufficiently simple system, there exist 3 constant values that you can use in the calculation that will actually produce optimal control in the system. These 3 numbers are different for every system and must be found out. There are many ways to find these numbers, however, I went with perhaps the most crude method, which is to simply guess at the values and then keep changing them until the control works. There is a method to this, however, and it is expressed in this series of 4 images. Each one of these graphs represents the step response given by the PID output, and it starts with setting the P constant to 1 and the I and D constants to 0. This effectively means that the output is exactly the error value. Although you can see this output will eventually stabilize, it will stabilize at the wrong value. The first step in what's called manual tuning is to raise the P value until the ball overshoots its target and begins to oscillate. It begins to oscillate when it reaches its target because the fan's power is correlated directly to the error value, and when the ball reaches its set point, the error value changes the sign. However, the ball will still most likely not settle at the right value. This necessitates adding in the integral term. By raising the integral term, the ball will eventually settle at the right location. However, this might take a long time, as the effect of overshoot can be quite disruptive. It is necessary to mention here that in the Labview implementation of the PID algorithm I use, it is not technically the Ki constant that is able to be set, but the period of integration that is modified. Instead of raising the weight of the Ki value, the integral term is controlled by modifying the period. After the P and I term are set, the ball will successfully be controlled. However, it will take a long time. Lots of people, when designing PID systems, stop here anyway, because the next term, the derivative term, which will ameliorate this problem, can introduce several problems itself. Derivatives are highly susceptible to high-frequency noise, as it's computed mainly by finding the slope between each position value, and this can mean the derivative term gives the wrong value if the measurement system is not adequate. In my case, however, the derivative term seems to behave properly, so I use it. You can see in the fourth picture that introducing the derivative term eliminates that overshoot. You can kind of visualize how this works by seeing that as the sensor measures from the top, a high positive derivative value would indicate that the ball is moving downwards, away from the top, rapidly. This high contribution to the PID would make the fan increase in power, slowing down the descent of the ball. It is this slowing effect that allows the ball to gracefully slide into its set point without overshoot, slowing down and stopping at just the right time. After all is said and done, the step response looks quite similar to the ideal step response. The final step is to take the somewhat arbitrary value output by the PID algorithm and get some usable duty cycle to give to the fan. I said before that below 30%, the fan would stall, so this is the minimum value I have. I set the maximum at 50%, as the fan really is quite powerful, so 50% is more than enough to get the ball moving up the tube pretty quickly. The PID algorithm outputs a number between -100 and 100, so I simply take this value and map it linearly between the duty cycles of 30 and 50%. -100 gives 30, 100 gives 50, and 0, for instance, would be right in the middle, so for a duty cycle of 40%. Here is the Labview implementation of the above algorithm and how it's interfaced to the hardware. I separated the code into 4 blocks, the blue block containing the code to initialize the DAC, the red block responsible for gathering the sensor data from the Vernier motion sensor, the yellow block for computing the result of the PID and sending it through the transfer function, and the green block for actually updating the duty cycle once its new value is calculated by the yellow block. There isn't too much to say about the initialization of the DAC. Most of the heavy lifting is done with these DAC blocks, which are basically just a low-level version of the DAC assistant. The actual DAC assistant can't be used here because changing the duty cycle on the fly requires some fidelity with the code. The code uses the hardware-generated counter pulse train output. The code to get the data from the motion sensor is already pre-written. Using the DAC assistant is more than what is needed. The position output is then sent to this PID block, which computes the aforementioned algorithm with the additional controls of the set point, the output range, which I have set to -100 to 100, and the PID constant values, Kp, Ki, and Kd. The 0.05 is the delta t in between samples. The Vernier motion sensor is set to collect 20 samples a second. The PID output goes to the transfer function, which is simply a linear function. Finally, that value updates the duty cycle local variable. To see the mechanics of how the duty cycle was updated, it is important to see the big picture in this code. The majority of the code exists in a while loop, with 2 independent processes happening every cycle. First, the position is read by the DAC, followed by the computation of the next pulse width modulated duty cycle, and eventually followed by the updating of what's called a local variable. The second process is that each cycle, this local variable will be read, along with the previous value of the duty cycle, stored in a shift register, and these 2 values are compared. Whenever the values are different, a case structure will be sent to value of true, which will initiate the process of modifying the duty cycle value in the actual hardware, which is just controlled by the DAC blocks. The future work that would be most productive for this project, I think, would be to figure out some way to actually mathematically model this system and in turn get some more sophisticated control systems than what was actually the most basic method possible, manually tuning a PID. My results were in fact able to control the ball, and while that is nice, it could certainly be done a lot faster. And there's a whole control systems theory built around doing just that for all sorts of different types of systems. As you can see here, the mathematical modeling that can be done into a system like this can get pretty intense. These equations come from a paper I found by some physicists who, for whatever reason, were also interested in how to effectively control the height of a ping pong ball in a tube with a fan. They found it necessary to model not just the physics of the ball, but also the physics of the fan, and further, to accomplish both of these tasks, had to experimentally find several constants, such as the drag coefficient of the ball, which would have frankly been impossible to accomplish among the other goals of this project. If the modeling can be done, however, the possibilities for creating a different control system does open up a lot.